To prepare us for a discussion of disaccharides, we now explore the concept of glycosides and glycoside bonds. So the way you get glycosides is if you take a pyranose form of glucose, just as we have seen in the last several lessons, and dissolve it in methanol. So this will give us the simple methyl glycoside in the presence of a small amount of acid. And a glycoside is an acetal rather than a hemiacetal. Okay, so we're starting with either the alpha or beta anomer of the glucopyranose. And what that little squiggle means, linking the anomeric carbon with its OH, that's chemical shorthand for we don't care which stereoisomer this is, it's going to do the same thing starting with either one. So the reaction will yield us either the alpha glucopyranoside or the beta glucopyranoside, both of them, of course, being the methyl acetals. So these two compounds are significantly different from each other. Of course, they are examples of being epimers, anomers, diastereomers. So the alpha has a melting point of 165 degrees. The beta has a melting point of 107 degrees. But look at the real difference in their optical rotations. The alpha has a specific rotation of positive 158 degrees, and the beta has a specific rotation of negative 33 degrees. So one of them's positive, the other's negative, and all we're doing is changing the stereochemistry at the anomeric carbon. The rest of the molecule's stereocenters remain the same, and it is still a D sugar. So, like any other acetal, glycosides are stable to basic conditions, but also like under other acetals, under aqueous acidic conditions, they will hydrolyze back to the cyclic hemiacetal form of the sugar and expel the alcohol as a leaving group. Okay, so the acetal form, the glycoside form, does not undergo mutarotation as like the normal cyclic hemiacetal does, but if you hydrolyze it, you will get back a mixture of the alpha and beta anomers. So when we look at the mechanism of this process, we're going to have to consider why we get a mixture of epimers at this stereocenter. Okay, so first we're going to look at the mechanism of glycoside formation, then on the next slide we'll look at the mechanism of glycoside hydrolysis. Okay, this mechanism should be fairly familiar to you because it is just like mechanisms that we looked at in the first semester when we looked at reactions of alcohols under acidic conditions. Okay, so the first step is to take the alcohol at the anomeric carbon and protonate it, that's why we need acid for this, to make it a good leaving group. And of course, all of these steps are reversible. So we protonate it to make it a good leaving group, then in step 2, we have our leaving group leave, and that's going to give us a resonance-stabilized oxocarbocation. So now that oxocarbocation, and what's drawn here in the center of your slide, is the resonance structure with the positive charge on the oxygen, which is of course the major resonance structure for an oxocarbocation. It can get attacked from either the top face or the bottom face. Okay, and what's the nucleophile that's going to do the attacking is methanol, because after all, we have dissolved this compound in methanol. So if you attack it from the top face, you end up going down the pathway that leads you towards the beta isomer. And if you attack it from the bottom face, you head down the pathway that leads you to the alpha isomer shown on the left. So in both of these cases, the initial attack of methanol leaves you with a compound that has an intermediate that has a positive charge on the oxygen, that oxygen still has its hydrogen because CH3OH is the nucleophile. We are under acidic conditions, so CH3OH has to be the nucleophile. There's no CH3O minus present. So we have the intermediate with the positive charge on oxygen, and then it's just simply going to lose a proton. It's going to get transferred to another molecule of methanol, but I did not show that explicitly, and that will give you the methyl glycoside product in each case. Glycoside hydrolysis is essentially the reverse of glycoside formation, and the steps and the rules governing them are exactly the same. So we start with the methyl glycoside, and then in this case, instead of acidic alcohol, we have aqueous acid, meaning that what you really have in solution is H3O+. H3O+ is going to serve as a proton source to protonate the OCH3. Can you protonate in other places in this molecule? Yes. Will that get you to where you want to go? No. So to get to where we want to go, we need to protonate the OCH3. So that will at some point happen. You've protonated it and made it into a better leaving group, and now it will leave as neutral methanol. This leads to the same resonance stabilized oxocarbocation that we saw previously in the middle of the mechanism of glycoside formation. But now, since we are doing the reaction in water as the solvent, there is a whole lot more water present than the molecule of methanol that you just kicked off. So water is going to come in, act as a nucleophile, and just like we saw in the previous slide with methanol, water can attack either the top face or the bottom face of this oxocarbocation. So if it attacks the top face, that's going to lead us to the beta anomer of glucopyranose, and if it attacks the bottom face, that will lead us to the alpha anomer. Just like in the mechanism of glycoside formation, we have an intermediate because water is attacking as a neutral nucleophile where the oxygen still has 3 bonds and a positive charge, and then that intermediate will get deprotonated by an additional molecule of water to give you the neutral hemiacetal product. Okay, so in many cases where we were talking about simple carbonyl groups, when you hydrolyzed an acetal, you would go all the way back to the aldehyde or ketone. In this case, the hydrolysis reaction will, for all intents and purposes, stop at the hemiacetal, because as we've already seen, the cyclic hemiacetal form is the favored form at equilibrium for many of the 6-carbon aldoses. Okay, so that's the basic mechanism of how a glycoside is formed and how a glycoside is hydrolyzed. We looked at the simple case of just forming a methyl glycoside. Now, as we move forward, we're going to start looking at when that which attacks is another sugar rather than methanol, which is going to lead us into the formation and hydrolysis of disaccharides.